Let's talk about how muscles can control the amount of tension. So, for example, I pick up one of these little markers. It doesn't take hardly any force at all to pick up one of these little markers, does it? Whereas I pick up a stool like this, it takes more force, all right? I don't know if you can see where the camera is. Look at my brachioradialis bulging out, my biceps brachii is contracted. I mean, it's not like this is terribly heavy, but it still takes more muscle tension, more force to pick up that than it does to pick up this, all right? See, there's no bulging of my muscles in this case. Bulging of my muscles. It's a disgusting thing to look at, but sorry, you signed up for this. So let's talk about, there are three basic ways that your muscles can control the amount of tension. For an individual muscle fiber, it's what we call wave summation, which is essentially the number of action potentials per second. It doesn't have to be per second, it's just per unit of time. Second was just convenient. We'll see coming up. And then for the entire muscle, we can control via the size of the motor unit and via the number of motor units recruited. Let's look at this one first. So when a muscle contracts, think about it. When I want to contract my forearm, when I want to flex my forearm, all right, it starts with a thought in my head. And I decide, okay, I want to flex my forearm right now. Well, a nerve signal has to travel down my spinal cord, out along a nerve, all right, like my musculocutaneous nerve, go to the muscle itself. That has to release neurotransmitter, that has to diffuse across the synaptic cleft, has to bind to the receptors, has to open the receptor. Sodium flows through, creates the muscle action potential, goes down the T-tubules, flows alongside the terminal cistern, calcium release channels open, calcium flows out, moves troponin, tropomyosin out of the way, then finally the myosin head can grab the actin filament and the muscle starts contracting. All that has to happen before the muscle actually starts to contract. So there's a slight delay. So if we look at a graph, we can call this a single twitch. A single twitch of a muscle, all right? Single twitch contraction, all right? Sort of full name. If we graph it, it looks like this. There's a little delay while all that stuff happens. Then we start to generate some force as myosin binds to actin. Then we get a maximum amount of force, and then as the myosin starts to let go, then the muscle relaxes and we go back to the resting state again. That's a single twitch contraction. That's what happens from the time that a muscle contracts until it stops contracting, okay? A single twitch contraction. Well, let's take a look at what would happen if, that would be if we sent out one action potential. What if we send out a bunch of action potentials in a row? What can happen in that case is that the muscle is starting to contract and maybe it's starting to relax, but then the second action potential shows up. Well, now the muscle is going to start contracting from here, and then another action potential shows up and now the muscle contracts from this point. So if we had a graph, all right, we'd be looking at time, and here we'd be looking at tension. So notice as time goes on, if a bunch of action potentials come all in a row, the muscle can only partly relax before the next action potential gets there. So the total amount of tension, instead of starting from zero, it starts from here. And therefore, several action potentials in a row generate more tension than just one does, okay? That's wave summation. That's how an individual muscle fiber can generate more force. It's by having more action potentials right in a row that keep building on each other to increase the amount of tension in that single muscle fiber, okay? So that's for an individual muscle fiber. Let's take a look now at an entire muscle. How does an entire muscle increase the amount of tension? Well, so here we have, you know, look out, he's drawing again. Oh my God, I apologize in advance. So here we have a single muscle fiber. Over here, oh God help us all. Let's draw three muscle fibers all right next to one another. All right, so, oh, I'm so sorry about this. All right, here are three muscle fibers all right alongside one another, okay? We'd have the little, you know, striations, remember? The little striations, okay, from the overlap of the thick and the thin filaments. This is ridiculous detail, not necessary. Okay, so let's say we have a motor neuron, all right, a single motor neuron that comes down and forms a neuromuscular junction with this muscle fiber. When we get an action potential coming down this motor neuron, it will cause this and only this muscle fiber to contract. But let's say over here we have a single motor neuron, but it branches and makes neuromuscular junctions with all three of these muscle fibers. What's going to happen now? A single action potential will cause all three of these muscle fibers to contract simultaneously. This is called a motor unit. The number of muscle fibers innervated by a somatic motor neuron is one motor unit. Now, if in your body it was only 1 versus 3 muscle fibers, that would hardly be noticeable. But in fact, in your body, it's anywhere from like 10 to 2,000. So in some cases, a single motor neuron activates 10 muscle fibers. One action potential causes 10 muscle fibers to contract. In other cases, a single action potential going to a large motor unit might cause 2,000 muscle fibers to contract. So there is going to be a lot more force of contraction, all right? And so that's the size of the motor unit. You have small motor units and large motor units, okay? Now, do you suppose those are equally distributed throughout your body? No, of course not. You have some muscles that need to do fine, precise, controlled, delicate movements. A lot of your muscles of speech, a lot of the muscles that control your fingers. I mean, you're doing, precise, controlled movements with your fingers. You tend to have small motor units. On the other hand, think of your vastus muscles on your legs that you jump and do things like that with. Those need to generate a lot of tension, a lot of force, a lot of contraction. So you tend to have big motor units in big powerful muscles like that, latissimus dorsi, muscles like that, huge motor units. Muscles that control the fingers and stuff like that, small motor units. Generally speaking, what your body does, by the way, well, let's pose a question. How does your body know when to use a small motor unit, when to use a large? Because that's what happens. Your body will either send out an action potential to a small motor unit or to a big one. A lot of that's just based on your experience with reality. So when you look at one of these markers, you decide ahead of time, well, that's not going to take much force. So you send out a signal on a small motor unit. On the other hand, if you're going to lift something like this stool, you're thinking, whoa, this is bigger, it's going to take more force. So you pick a bigger, now you don't do it consciously, but your brain does that for you, thank God. Because if you did it consciously, you'd screw it up, just like you've screwed up everything else in your life. But your brain then decides to use a larger motor unit. And sometimes, you can get fooled. Have you ever gone to pick something up that you thought was going to be heavy and it turned out not to be? And you picked it up and you're like, whoa! Use way too much force. Or the opposite can happen. You think it's not going to be very heavy and you go to pick it up and you're like, yeah. So you can misjudge. In that case, what happens? Well, it's the number of motor units recruited. Generally speaking, your brain will start by going for small motor units. Figure it's better, not to lose your balance overcompensating for something, overpowering. So generally, your body starts by using small motor units. And if that can't get the job done, then your body recruits more. All right, recruit, like in the military, recruits means you, soldier, in the kitchen, peel those potatoes. So you're recruited to do something. So again, your body will have different size motor units. It will generally start with the smaller ones. If that doesn't work, then it'll keep using bigger and bigger ones. So I start moving this wall, yeah, my body's going to keep recruiting until finally we're going, yeah, the wall's not going to move. Let's just quit, have a beer. So there you go. That's how you control muscle tension, 3 basic ways. You can control it in an individual muscle fiber by wave summation. And then in the entire muscle, you can control it by the size of the motor unit and the number of motor units recruited. All 3 of these combine together to allow you to have pretty good control over the amount of muscle tension that you use to do something. And I think I'll use some muscle tension right now to go get a beer.